Back in 1935, Einstein presented a thought experiment. It revealed something surprising. Quantum mechanics appeared to violate one of the most fundamental rules in physics, that nothing can travel faster than the speed of light. Most physicists assumed Einstein had made a mistake. They believed that at 56 years old, he was simply past his peak, unable to embrace this radical new theory. But 3 decades later, one scientist discovered Einstein's forgotten paper. He realized something important. The prediction could actually be tested. When the experiments were finally performed, the results were astonishing. Quantum physics really does seem to break the universal speed limit. We are compelled to consider something like actions traveling faster than light from one location to another. This is a story about one of the strangest and most misunderstood experiments in all of physics. It might even be the strongest evidence we have that we live in many worlds. But to understand why this discovery was so shocking, we need to understand what came before. We need to understand why physicists believed so strongly that nothing could travel faster than light. This belief didn't come from nowhere. It was built on centuries of careful observation and deep mathematical reasoning. The speed limit of the universe emerged from one of the greatest intellectual revolutions in human history. The speed of light has always held a special place in physics. For centuries, scientists debated whether light traveled instantaneously or if it had a finite speed. Ancient Greek philosophers had different views on this question. Empedocles believed light must take time to travel, while Aristotle argued that light propagation was instantaneous. The debate continued for nearly 2,000 years. In the 17th century, a Danish astronomer named Ole Rømer was studying the moons of Jupiter. He noticed something peculiar. The timing of the eclipses seemed to shift depending on where Earth was in its orbit. When Earth was moving toward Jupiter, the eclipses appeared to happen earlier than predicted. When Earth was moving away, they appeared later. Rømer was studying Io, the innermost of Jupiter's 4 largest moons. Io orbits Jupiter every 42.5 hours, passing in and out of Jupiter's shadow with clockwork regularity. Or so it seemed. Rømer kept careful records of these eclipses over many months. He noticed that the eclipses would gradually drift earlier in the year when Earth was moving toward Jupiter in its orbit. Then they would drift later when Earth was moving away. The pattern was consistent and measurable. The cumulative difference amounted to about 22 minutes over the course of Earth's year-long orbit. Rømer realized what this meant. The light carrying the image of Io's eclipse had to travel different distances depending on where Earth was in its orbit. When Earth was closer to Jupiter, the light had less distance to travel. When Earth was farther away, the light had more distance to travel. Rømer realized what this meant. Light must have a finite speed. The delays he observed were caused by the changing distance light had to travel. His calculations suggested that light moved at about 220,000 kilometers per second. Not quite accurate by modern standards, but remarkably close for the time. This was the first real evidence that light had a speed limit. The announcement of this discovery in 1676 was met with skepticism by many scientists. The idea that light had a measurable speed was revolutionary. But over time, as more observations confirmed Rømer's findings, the scientific community came to accept that light does indeed travel at a finite speed. Over the next 2 centuries, measurements became more and more precise. In 1849, French physicist Hippolyte Fizeau devised an ingenious experiment. He placed a rapidly rotating toothed wheel between a light source and a distant mirror. Light would pass through a gap in the wheel, travel to the mirror, and return. If the wheel rotated at just the right speed, the returning light would be blocked by the next tooth. By measuring the rotation speed, and knowing the distance to the mirror, Fizeau calculated the speed of light. His result was about 315,000 kilometers per second, closer to the true value than Römer's estimate, but still not quite right. A few years later, Léon Foucault improved on Fizeau's method, using a rotating mirror instead of a toothed wheel. His measurements gave a speed of about 298,000 kilometers per second, much closer to the modern value. By the late 1800s, physicists had determined that light travels at approximately 300,000 kilometers per second in empty space. This number would become one of the most important constants in all of physics. Scientists gave it a special symbol, the letter C. But back then, no one understood why this speed was so special. No one knew it represented an absolute cosmic speed limit that nothing could exceed. The most precise measurements came from American physicist Albert Michelson. He was obsessed with measuring the speed of light with ever greater accuracy. He developed sophisticated techniques using rotating mirrors and long baseline measurements. His work earned him the Nobel Prize in 1907, becoming the first American to win the prize in science. Michelson's measurements converged on a value of about 299,792 kilometers per second. This is remarkably close to the modern accepted value of 299,792.458 kilometers per second. Today, the speed of light is actually defined to be exactly 299,792,458 meters per second. We use this to define the meter itself. But why is this speed so important? What makes light special? In the 1860s, James Clerk Maxwell developed equations that unified electricity and magnetism into a single electromagnetic theory. These equations predicted that electromagnetic waves should propagate at a specific speed. When Maxwell calculated this speed using measured values of electric and magnetic constants, he got a number very close to the measured speed of light. This was a stunning revelation. Light is an electromagnetic wave, and Maxwell's equations predicted that all electromagnetic waves, regardless of their source or frequency, should travel at the same speed in empty space. This was a deep theoretical result, with far-reaching implications that wouldn't be fully understood for another 40 years. Imagine the sun were to suddenly vanish. How long would it take before we noticed and were flung out into space? According to Newton's theory, gravity acts instantly across any distance. So, if there's a change in gravity, we should feel it right away. But Newton himself found this idea troubling. He once wrote that the notion of one body acting upon another at a distance was so absurd that he believed no one with competent thinking could accept it. Newton's laws of motion and gravity had transformed science. Published in 1687, his mathematical framework could predict the motion of planets, the trajectory of cannonballs, and the fall of apples with stunning accuracy. For over 200 years, Newton's laws reigned supreme. They seemed to describe the universe perfectly. The Principia Mathematica, Newton's great work, contained his 3 laws of motion and his law of universal gravitation. These simple mathematical statements could explain everything from the orbits of planets to the tides of the oceans. Astronomers used Newton's laws to predict the positions of planets years in advance with remarkable precision. Engineers used them to design machines and structures. The laws seemed universal and eternal, but Newton knew there was something philosophically unsatisfying about his theory. How could the sun reach across the vast emptiness of space and pull on Earth without anything connecting them? How did Earth know the sun was there? Newton had no answer. He simply described what gravity did, not how it worked. In his own words, he declined to frame hypotheses about the mechanism. The mathematics worked, and that was enough. In a letter to Richard Bentley in 1692, Newton expressed his discomfort more fully. He wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it. Yet despite this philosophical unease, Newton's theory worked too well to abandon. It explained too much, predicted too accurately. So physicists accepted action at a distance as a mysterious but undeniable feature of nature. Some tried to explain it with invisible fluids or ethers permeating space. But none of these explanations were satisfactory or necessary for practical calculations. Yet this idea of instant action at a distance nagged at physicists for generations. If you moved the sun, how would Earth know to change its orbit? According to Newton's equations, it would know immediately, no matter how far away Earth was. This seemed to violate common sense. After all, everything else in nature takes time to propagate. Sound waves travel through air at a finite speed. Water waves ripple outward from their source. Why should gravity be different? Consider other forces we experience in daily life. When you push a door, the door moves, but the force doesn't act instantly throughout the entire door. It propagates as a compression wave through the material. When you snap a whip, the wave travels along its length at a finite speed. When you speak, sound waves carry your voice to a listener at about 340 meters per second. Everything we observe has a causal structure where effects propagate at finite speeds. Electricity and magnetism also seemed to propagate at finite speeds. When you flip a light switch, there's a tiny delay before the light bulb illuminates as the electrical signal travels through the wire. Electromagnetic waves like radio and light travel at a specific, measurable speed. Only gravity seemed different, acting instantly across vast distances. Then in 1905, Einstein realized something crucial. Action at a distance is not just absurd, it leads to genuine paradoxes. Einstein had discovered that observers moving at different speeds can disagree about when events occur. Let's say you witness two things happening at the same moment. An observer speeding past you would see it differently. To them, one event happened first. Both perspectives are equally valid. But when we apply this to gravity, we run into serious problems. Einstein's insight came from thinking deeply about light and motion. He had been puzzling over a question since he was 16 years old. What would you see if you could ride alongside a beam of light? According to classical physics, if you moved at the speed of light, the light wave should appear frozen, stationary, relative to you. But Maxwell's equations, which describe light as an electromagnetic wave, suggested this was impossible. There seemed to be no such thing as a stationary light wave. For 10 years, this paradox bothered Einstein. He thought about it constantly. He discussed it with friends and colleagues. He tried different approaches to resolve it. Nothing worked. Then, in 1905, while working as a patent clerk in Bern, Switzerland, Einstein had a breakthrough. He realized that the problem was not with Maxwell's equations. The problem was with our assumptions about space and time. Einstein's 1905 paper on special relativity began with a simple statement. The laws of physics are the same for all observers moving at constant velocity relative to each other. And the speed of light in empty space is the same for all observers, regardless of their motion. These two postulates, simple as they sound, completely revolutionize our understanding of space and time. This paradox led Einstein to a radical conclusion. The speed of light must be the same for all observers, regardless of how fast they're moving. This sounds simple, but its implications are profound. If light always travels at the same speed relative to you, then something else has to give. That something is time itself. Time, Einstein realized, is not absolute. It flows at different rates for observers moving at different speeds. What seems simultaneous to one observer might not be simultaneous to another. This is called the relativity of simultaneity, and it completely changes how we think about cause and effect. The implications are extraordinary. If you're moving fast enough, your clock runs slower relative to a stationary observer. This is called time dilation, and it's been confirmed by countless experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground. Particles moving at high speeds in accelerators live longer than they should according to their natural decay rates. GPS satellites must account for time dilation effects, or they would accumulate errors of several kilometers per day. There's also length contraction. Objects moving at high speeds are compressed in the direction of motion. A spaceship traveling at 90% the speed of light would appear shortened by more than half to a stationary observer. Space itself contracts. These are not optical illusions or measurement errors. They are real physical effects predicted by relativity and confirmed by experiment. The famous twin paradox illustrates how strange this can be. Imagine twins. One stays on Earth, while the other travels to a distant star and back at high speed. When the travelling twin returns, she has aged less than her sibling who stayed home. This is not just a thought experiment, it's been verified with atomic clocks on airplanes and satellites. Time really does flow at different rates depending on your motion. Imagine you see the sun disappearing and Earth flying off at the same instant, just as Newton predicted. The other observer sees something impossible. They see Earth flying off first, even while the sun is still present and should be pulling Earth inward. To them, it appears that cause and effect are reversed. This is more than just a philosophical problem. If cause and effect can be reversed, then logic itself breaks down. You could have situations where an effect happens before its cause. In the most extreme cases, you could create time paradoxes where future events influence past events. The universe would become inconsistent, governed by contradictions. The only way to resolve this paradox is to reject our starting assumption. Gravity cannot be instantaneous. It took Einstein 10 years to solve this problem. In the process, he completely transformed our understanding of gravity. Gravity is caused by the bending of space-time. When there's a change in gravity, it only affects the local space-time. Then that disturbance spreads outward to nearby regions, which spread farther out, until eventually the ripple reaches us. Those 10 years from 1905 to 1915 were incredibly difficult for Einstein. Special relativity had explained motion at constant velocity, but what about acceleration? And how could gravity fit into this new picture? Einstein struggled with the mathematics. He taught himself advanced tensor calculus. He collaborated with mathematician Marcel Grossmann to develop the necessary geometric framework. The breakthrough came when Einstein realized that gravity is not a force in the traditional sense. It's the curvature of space-time itself. Massive objects don't pull on other objects. Instead, they curve the space around them, and other objects follow the curves. This is general relativity, and it's one of the most beautiful theories in all of physics. Einstein called his new theory general relativity. In this framework, mass and energy curve the fabric of space-time itself. Imagine space-time as a stretched rubber sheet. Place a heavy ball on the sheet, and it creates a dip. Smaller objects rolling nearby will curve toward the dip, not because the ball is pulling them, but because the sheet itself is curved. This is how gravity works. Objects follow the curves in space-time. The rubber sheet analogy is helpful but imperfect. Real space-time is 4-dimensional, not 2-dimensional. It involves time as well as space. And the curvature can be complex, with ripples and waves. But the basic idea holds. Massive objects curve space-time, and this curvature is what we experience as gravity. The mathematics of general relativity is elegant but complex. Einstein's field equations relate the curvature of space-time to the distribution of mass and energy. These equations are nonlinear differential equations that are notoriously difficult to solve. Even Einstein could only solve them exactly for a few simple cases. But the theory made several predictions that could be tested. When something massive moves or changes, it creates ripples in space-time that spread outward like waves on a pond. These are called gravitational waves. Einstein predicted their existence in 1916, though they wouldn't be directly detected for another century. In 2015, the LIGO Observatory detected gravitational waves from 2 black holes colliding over 1 billion light-years away. It was one of the great experimental confirmations in physics, proving that gravity really does travel at the speed of light. The detection of gravitational waves was a triumph of experimental physics. LIGO uses laser interferometry to detect tiny changes in space-time. When a gravitational wave passes through, it stretches space in one direction and compresses it in the perpendicular direction. The amount of stretching is incredibly small. The detectors must be sensitive enough to measure changes smaller than 1,000th the diameter of a proton across a 4-kilometer baseline. On September 14, 2015, both LIGO detectors in Louisiana and Washington detected a signal. The waveform matched theoretical predictions for 2 black holes spiraling together and merging. One black hole was about 29 times the mass of our Sun, the other about 36 times. When they merged, they released more power than all the stars in the observable universe combined, though only for a fraction of a second. The gravitational wave travelled for over 1 billion years across space before reaching Earth. By the time it arrived, it had weakened tremendously, but LIGO was sensitive enough to detect it. This discovery opened a new window on the universe. We can now observe cosmic events through gravitational waves, not just light. It's like gaining a new sense. This theory of gravity is local because effects spread from place to place at the speed of light instead of being instant. If the sun disappeared, that ripple would take about 8 minutes to reach us. Another observer might disagree about the length of the delay, but now everyone agrees that the sun disappeared first. This is why nothing can exceed the speed of light. The delay between cause and effect ensures all observers agree on the sequence of events. The speed of light is not just a speed limit for objects. It's a speed limit for causality itself. It's the speed at which cause and effect can propagate through the universe. Nothing can travel faster than light because if it could, causality would break down. We would have paradoxes and contradictions. The universe would stop making sense. In relativity, the speed of light emerges as something even more fundamental than just how fast light travels. It's the universal conversion factor between space and time. It's the speed at which massless particles must travel. It's the ultimate speed limit woven into the fabric of reality itself. Any particle with mass can approach but never reach the speed of light. Only massless particles, like photons, travel at exactly this speed. As objects approach the speed of light, strange things happen. their mass appears to increase, requiring ever more energy to accelerate further. Time dilation becomes extreme. A spaceship traveling at 99.9% the speed of light would experience time passing 22 times slower than on Earth. Travel to a star 10 light-years away and back at this speed, and you would age less than a year while decades passed on Earth. These effects have been measured countless times. Cosmic ray particles called muons are created in Earth's upper atmosphere. They decay so quickly that they should never reach the ground, even travelling at near light speed. But because of time dilation, they live longer from our perspective and do reach the surface. Every day, cosmic ray experiments verify Einstein's predictions. Particle accelerators routinely accelerate particles to 99.9999% to the speed of light. The particle's behavior precisely matches relativistic predictions. Their increased mass requires ever more powerful magnets to bend their paths. Their extended lifetimes allow unstable particles to travel farther before decaying. Relativity is not just a theory, it's engineering reality at places like CERN and Fermilab. The speed limit of light is not an arbitrary cosmic rule. It emerges from the deep structure of space-time itself. Space and time are not separate entities, but aspects of a single four-dimensional space-time. The speed of light is the conversion factor between the space dimensions and the time dimension. It's woven into the metric of space-time, the mathematical object that defines distances and durations. After Einstein corrected gravity, all of classical physics followed this important principle. Locality seemed secure. Causality was protected. The universe made sense. But then something unexpected happened. A new theory was emerging that would challenge everything physicists thought they understood about reality. The quantum revolution began quietly in 1900. Max Planck was trying to explain the spectrum of light emitted by hot objects. Classical physics predicted infinite energy at short wavelengths, an absurd result called the ultraviolet catastrophe. Planck found he could fit the data if he assumed energy came in discrete chunks or quanta. He thought this was just a mathematical trick. It wasn't. In 1905, the same year he developed special relativity, Einstein extended Planck's idea. He proposed that light itself comes in discrete packets, later called photons. This explained the photoelectric effect, where light knocks electrons out of metal. Only light above a certain frequency can do this, regardless of brightness. If light were a continuous wave, any brightness should eventually knock electrons free. But if light comes in photons, each carrying a specific energy, then only high-frequency photons carry enough energy. This work earned Einstein the Nobel Prize in 1921. Then in 1913, Niels Bohr proposed that electrons in atoms occupy discrete energy levels. Electrons can only exist at certain distances from the nucleus, not anywhere in between. When electrons jump between levels, they emit or absorb light at specific frequencies. This explained the spectrum of hydrogen and other atoms, patterns that had puzzled scientists for decades. By the 1920s, physicists realized they needed a new framework. Classical physics could not explain atoms. Electrons orbiting nuclei should radiate energy and spiral inward in a fraction of a second. Atoms should be unstable, yet atoms exist. Something was fundamentally wrong with classical physics at small scales. The breakthrough came in 1925 and 1926. Werner Heisenberg developed matrix mechanics, a mathematical framework based on observable quantities. Independently, Erwin Schrödinger developed wave mechanics, treating particles as waves evolving according to a wave equation. These approaches looked completely different, but turned out to be mathematically equivalent. By 1927, quantum mechanics was essentially complete in its mathematical form. The theory made predictions that agreed with experiments to stunning precision, but nobody understood what it meant. The mathematics worked, but the physical interpretation was murky and deeply puzzling. That's why the Solvay conference was convened, to figure out what this strange new theory was telling us about reality. But then Einstein examined the new theory of quantum mechanics and made an unsettling discovery. This is one of the most famous photographs in physics. It was taken at the 1927 Solvay conference, where the pioneers of the brand new quantum theory gathered to discuss their work. Around 60% of those present would eventually win Nobel Prizes. But Einstein believed they had gotten something fundamentally wrong, and this was his opportunity to prove it. The Solvay conferences were invitation-only gatherings of the world's leading physicists. They were held in Brussels, funded by the Belgian industrialist Ernest Solvay. The 1927 conference focused entirely on the new quantum theory, which was barely 2 years old in its modern form. The conference lasted a week, and the discussions were intense. The attendees included some of the greatest minds in physics. There was Marie Curie, the only woman present who had won 2 Nobel Prizes in 2 different fields. There was Max Planck, whose work on blackbody radiation had started the quantum revolution. Paul Dirac, who would later predict antimatter, sat quietly in the back row. Wolfgang Pauli, known for his sharp criticism, was there to challenge every idea. Erwin Schrödinger was also present, though he would later become deeply uncomfortable with the Copenhagen interpretation. Louis de Broglie, who proposed wave-particle duality, attended and presented his ideas. Max Born, who developed the probability interpretation of the wave function, was there. Arthur Compton, whose work on X-ray scattering provided evidence for photons, participated in the discussions. And then there were the 2 main figures in our story. Niels Bohr, 42 years old, confident and philosophical, and Albert Einstein, 48 years old, increasingly skeptical of the theory he had helped create. The stage was set for one of the great intellectual battles in the history of science. During the day, the conference featured formal presentations and discussions. In the evenings, informal debates continued at dinner and in hotel rooms. Einstein would propose clever thought experiments designed to show inconsistencies in quantum mechanics. Bohr would spend hours analysing these proposals, often pacing back and forth, struggling to find the flaw in Einstein's reasoning. By morning, Bohr would have a response. So he took the stage with a thought experiment. Imagine you fire a single electron through a narrow slit toward a circular detection screen. Quantum mechanics says that this electron has a wave associated with it, called a wave function, which spreads out through space as it travels. When the electron hits the screen, you detect it at a single point. Where it appears depends on the amplitude of the wave. If the wave is very large in a particular area, the electron is more likely to appear there. This wave-particle duality was one of the strangest aspects of quantum mechanics. Electrons, which everyone thought were particles, seemed to also behave like waves. This had been demonstrated experimentally. If you fire electrons one at a time through 2 slits, they create an interference pattern on the screen behind, just like waves do. But each electron is detected as a single point, like a particle. The double slit experiment is perhaps the most famous demonstration of quantum weirdness. When you close one slit and fire electrons through the other, they accumulate in a pattern that makes sense for particles. They form a blob on the screen, roughly aligned with the open slit. When you open both slits, you might expect the pattern from each slit to simply add together. But that's not what happens. Instead, you get an interference pattern, alternating bands of light and dark, just like waves interfering with each other. Some regions get many electrons, others get almost none. The dark bands are places where the waves from the two slits cancel out. The bright bands are where they reinforce. This makes sense if electrons are waves passing through both slits simultaneously. But here's the paradox. When you detect electrons at the screen, you always detect whole electrons, never fractions. Each electron leaves a single dot on the screen. If you fire electrons one at a time, very slowly, the dots appear randomly scattered at first. But as more and more electrons arrive, the interference pattern gradually emerges. Each individual electron somehow knows about both slits, even though it seems to go through one or the other. If you try to determine which slit each electron goes through by placing detectors at the slits, the interference pattern disappears. The act of measurement changes the outcome. This is deeply puzzling. It suggests that the electron is doing something fundamentally different when observed versus when not observed. The wave function describes all the possible places the electron might be found. It spreads out across space, assigning a probability to each location. The mathematics was elegant and precise. But what did it mean physically? Was the electron really spread out like a wave? Or was it always at a definite location, and the wave function just represented our ignorance? Let's say it appears here. So far, everyone was following. This is what quantum mechanics predicts. But Einstein's next question caught them off guard. Why doesn't the electron appear at this other spot a moment later? There's only one electron, so we cannot detect it twice. But the way quantum mechanics ensures this is that when the electron was detected at the first spot, its wave function collapsed to zero everywhere else, instantly. That's why the probability of finding it at the second spot is now zero. There's no longer any wave present there. But Einstein asked the audience to consider what this means. The measurement here must instantly affect the wave function over there, no matter how far apart these locations are. In other words, quantum mechanics requires instant influences across distance. It violates locality. Einstein concluded his talk by saying this is an entirely peculiar mechanism of action at a distance, and that this implies, to his mind, a contradiction with the postulate of relativity. The room fell silent. Einstein's argument was elegant and simple, perhaps too simple. He had identified what seemed to be a fundamental inconsistency in quantum mechanics. The theory required faster-than-light influences, yet Einstein's own relativity forbade such things. Something had to give. Einstein's argument was so simple, and his talk so brief, that people didn't know how to respond. One audience member said he felt himself in a very difficult position because he did not understand what precisely Einstein wanted to make clear. No doubt it was his fault. That man was Niels Bohr, the most influential figure in quantum physics at the time. Bohr's Institute in Copenhagen had become the center for this new field. Dozens of young scientists, like Werner Heisenberg, came to learn from him. As one of his students remembers, Bohr had invited a number of them to his home, where they sat close to him, some literally at his feet on the floor so as not to miss a word. The relationship between Bohr and Einstein was complex. They had deep respect for each other, yet they disagreed profoundly about the nature of reality. Bohr believed that quantum mechanics was complete, that it told us everything physics could tell us. Einstein believed there must be something deeper, some hidden layer of reality that quantum mechanics failed to capture. Their debates would continue for years, through letters and papers, at conferences and private meetings. Each exchange sharpened the arguments on both sides. Einstein would propose a thought experiment designed to reveal a flaw in quantum mechanics. Bohr would carefully analyze it and show why it didn't work. Then Einstein would refine his argument and try again. One famous exchange involved what's called the photon box experiment. Einstein imagined a box containing photons, with a shutter that could open briefly to let a single photon escape. By weighing the box before and after, using Einstein's own equation, E equals mc squared, you could determine the photon's energy. By measuring when the shutter opened, you could determine the time of emission. This would seem to violate Heisenberg's uncertainty principle, which says you cannot know both energy and time precisely. Bohr spent a sleepless night analyzing this proposal. By morning, he realized that Einstein had overlooked something. The act of weighing the box in a gravitational field affects the rate of time flow according to general relativity. When you account for this gravitational time dilation, the uncertainty principle is preserved. Einstein had been beaten by his own theory, yet even this didn't settle the debate. Bohr was not the one who wrote the mathematical rules of quantum mechanics. Instead, he told everyone what they meant. While others were confused by the theory, Bohr offered answers. His philosophy became known as the Copenhagen interpretation of quantum mechanics. The general understanding of the Copenhagen interpretation is this. You have the wave function. It describes everything that you can know about a particle or a system, and it evolves according to the Schrödinger equation. At some point, you're going to make a measurement, and at that point, the wave function collapses. I think one important bit is that the wave function is all you can know about the particle. That was a pretty important point to Bohr. As Bohr would put it, it's wrong to think that the task of physics is to find out how nature truly is. The job of physics is just to predict measurements in the lab, which quantum mechanics does incredibly well. As for what the electron is doing when you're not looking, well, to Bohr, that question did not even make sense. This was a radical philosophical stance. For centuries, physicists had assumed that their job was to describe reality as it actually is. A particle has a definite position and velocity, whether we measure it or not. The moon is there even when no one is looking at it. But Bohr was suggesting something different. Maybe physics can only describe what we observe, not what exists independently of observation. Bohr's philosophy was influenced by the principle of complementarity. Wave and particle are complementary descriptions. You can measure wave properties or particle properties, but not both simultaneously. Which one you observe depends on your experimental setup. The electron is neither wave nor particle in any absolute sense. It's something that exhibits different aspects depending on how you choose to look at it. The wave function tells you everything physics can or should tell you. Einstein could not stand the Copenhagen interpretation. In a letter to his ally Schrödinger, he called it a tranquilizing philosophy or even a religion. Einstein felt his thought experiment exposed a critical weakness in the Copenhagen interpretation. He had shown that the way the wave function collapses is non-local. And so he reasoned, maybe the wave function is the problem. Maybe it's not the best way to describe the electron. Einstein believed in realism, the idea that objects have definite properties independent of whether we measure them. He also believed in locality, that objects can only influence nearby objects, and influences take time to propagate. These principles had guided all of classical physics. But quantum mechanics seemed to violate one or both of them. To Einstein, this meant quantum mechanics was incomplete. In a famous quote from 1926, Einstein wrote to Max Born, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice." This last phrase, often shortened to "God does not play dice," became Einstein's most famous objection to quantum mechanics. He wasn't making a religious argument. He was expressing his conviction that the universe operates according to deterministic laws, not random chance. Quantum mechanics says that some events are fundamentally unpredictable, that nature really is governed by probability. Einstein refused to accept this. After all, he may not have convinced Bohr during his talk, but he was determined to continue the debate during the rest of the conference. Physicists tell a version of this story that you will find in physics, textbooks, and in popular science books. It's a story physicists tell amongst themselves. What happened was Einstein and Bohr had a great debate. Einstein was unhappy with quantum mechanics because it was fundamentally probabilistic. He tried to show that there were conceivable experiments that you could use to get around those uncertainty relations, and Bohr showed over and over again that you could not do that. Eventually, Einstein gave up and accepted quantum mechanics. Well, that's not really what happened. The real story is quite different. At the end of the conference, Einstein probably did believe that Bohr was right. But as he thought about it more deeply over the next several years, he became convinced that there was something fundamentally wrong with quantum mechanics. In 1935, Einstein wrote a paper with two younger colleagues, Boris Podolsky and Nathan Rosen. It's now known as the EPR paper, named after their initials. This paper refined Einstein's earlier thought experiment and made it even more powerful. The EPR paper was published in a journal called Physical Review. Its title was simple and direct: Can quantum mechanical description of physical reality be considered complete? The paper's argument was carefully constructed, more rigorous than Einstein's earlier talks. It defined what it meant for a theory to be complete and what it meant for something to be an element of physical reality. Then it showed that quantum mechanics could not satisfy both conditions simultaneously. The paper began with a definition of reality. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. This seems like a reasonable criterion. If you can predict something with certainty without measuring it, then it must be real. Imagine a special radioactive atom sitting perfectly still. Suddenly, it decays into an electron and a positron that fly off in opposite directions. Since the original atom was at rest, the electron and positron must have equal and opposite momentum. The electron flies to the left, the positron flies to the right. We can measure these particles at two distant locations, and quantum mechanics says that before we measure them, we don't know which way the electron is spinning. It's in a superposition of spinning up and spinning down. But here's the key point. Because they came from the same atom, their spins are always opposite. If you measure the electron and find it spinning up, the positron must be spinning down. This is called entanglement. The states of the two particles are linked, even though they're far apart. Entanglement is perhaps the most distinctive feature of quantum mechanics. It has no analogue in classical physics. When particles become entangled, they lose their individual identities, in a sense. You can no longer describe each particle separately. You must describe them as a single system, even if they're separated by enormous distances. The mathematics of entanglement is precise and well understood, but its physical interpretation remains deeply puzzling. What does it mean for two particles to be entangled? Are they connected by some invisible thread? Do they communicate with each other somehow? Or is entanglement telling us something even stranger about the nature of reality? Schrödinger coined the term entanglement in a paper responding to EPR. He called it the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Schrödinger was deeply troubled by entanglement, perhaps even more than Einstein. He saw it as the defining mystery of quantum mechanics. Now Einstein asked, what happens when you measure one of them? Let's say you measure the electron and find it spinning up. Quantum mechanics says that the moment you measure the electron, the positron's wave function must collapse to spinning down, even though it could be light years away. But how does the positron know that the electron was just measured? How does it know to collapse to down instead of up? It seems like the electron must send some kind of signal to the positron, faster than light, telling it what happened. Einstein argued that this was absurd. Relativity forbids faster than light communication. So he concluded that quantum mechanics must be incomplete. There must be some deeper theory that doesn't require these instant influences. Einstein suggested that maybe each particle already has a definite spin, even before we measure it. We just don't know what it is. These unknown properties are called hidden variables. If hidden variables exist, then there's no need for faster than light influences. The particles don't need to communicate. They already knew what their spins were all along. We were just ignorant of them. Think of it like this. Imagine you have a pair of gloves, one left-handed and one right-handed. You put each glove in a separate box and send them to opposite sides of the galaxy. When someone opens the first box and finds a left-handed glove, they immediately know the other box contains a right-handed glove. But nothing faster than light happened. The gloves were always left-handed and right-handed. We just didn't know which was which until we looked. Einstein suggested that quantum particles work the same way. The electron was always spinning up, and the positron was always spinning down. Quantum mechanics just couldn't tell us this in advance. It's a theory of our knowledge, not of reality itself. This view became known as local hidden variable theory. Local because it respects the speed of light limit, and hidden variable because it assumes particles have definite properties we can't see. Most physicists rejected this idea. They believed the Copenhagen interpretation was correct, but for years, nobody knew how to test who was right. The debate remained purely philosophical. It seemed impossible to distinguish between Einstein's view and Bohr's view experimentally. Both theories made the same predictions for all known experiments. The debate became a matter of interpretation and philosophy, not testable science. Many physicists lost interest. They focused on using quantum mechanics to make predictions, not on arguing about what it meant. The years following the EPR paper saw quantum mechanics mature into a practical tool. Physicists used it to understand atomic structure, chemical bonding, and solid-state physics. During World War II, quantum mechanics was essential for developing radar and nuclear weapons. After the war, it enabled the invention of the transistor, the laser, and countless other technologies. Quantum mechanics worked brilliantly for practical applications, but the foundational questions remained unanswered. What is the wave function really? Does it represent reality or just our knowledge? Is there a hidden layer of reality beneath quantum mechanics? Most physicists adopted a pragmatic attitude. Shut up and calculate. Use quantum mechanics to solve problems. Don't worry about interpretation. Einstein became increasingly isolated in his views. Younger physicists regarded him as out of touch, clinging to outdated ideas about reality. The quantum revolution had left him behind, or so it seemed. But Einstein never wavered in his conviction that something was wrong. He continued to think about these problems for the rest of his life, even as most of the physics community moved on. Einstein spent his later years at the Institute for Advanced Study in Princeton, working on unified field theory. He was trying to combine gravity and electromagnetism into a single framework, hoping this might reveal the hidden reality beneath quantum mechanics. He never succeeded, Some colleagues felt he was wasting his time on a fool's errand, but Einstein remained convinced that there must be a deeper, more complete description of nature. Then in 1964, a physicist named John Bell was working at CERN. During his free time, he started thinking about the EPR paper. Bell wondered if there was a way to distinguish between Einstein's hidden variable theory and standard quantum mechanics. Could you design an experiment that would give different results depending on which theory was correct? John Stuart Bell was born in Belfast, Northern Ireland, in 1928. He grew up in a working-class family and showed an early aptitude for mathematics and physics. He earned his doctorate from the University of Birmingham and went on to work at CERN, the European Particle Physics Laboratory near Geneva. Most of his professional work involved particle physics, but in his spare time, he thought about the foundations of quantum mechanics. Bell was troubled by the same issues that had bothered Einstein. He felt that the Copenhagen interpretation was philosophically unsatisfying. He wanted to understand what was really happening at the quantum level, not just how to make predictions. So he read the EPR paper carefully and thought about whether Einstein's hidden variable idea could be tested. Bell's interest in quantum foundations was somewhat unusual for his time. Most physicists considered such questions a waste of time. The attitude was that quantum mechanics worked, so why worry about interpretation? But Bell disagreed. He believed that understanding what the theory means is essential to doing good physics. Interpretation guides intuition, which guides research. Bell discovered something remarkable. He proved that any hidden variable theory that respects locality, meaning no faster than light influences, must satisfy certain mathematical constraints. These are now called Bell inequalities. Then he showed that quantum mechanics violates these inequalities. This meant that you could test the predictions in a lab. The key insight was to measure the particles along different angles. In the original EPR thought experiment, you might measure both particles along the same axis, say vertical. But what if you measure them along different axes? One vertical, one horizontal, one diagonal? Bell showed that the pattern of correlations you observe depends on whether hidden variables exist. If particles have definite hidden properties, then the correlations must obey certain mathematical limits. These limits are the Bell inequalities. But quantum mechanics predicts correlations that violate these limits. So by performing the right measurements, you can determine which theory is correct. The mathematics behind Bell's inequality is surprisingly simple, at least in its basic form. Imagine you have 3 possible measurement settings for each detector. Call them A, B, and C. You measure pairs of particles, sometimes with both detectors set to A, sometimes one at A and one at B, and so on. You count how often the results agree versus disagree for each combination. Bell showed that if local hidden variables exist, the correlations must satisfy a simple inequality. Roughly speaking, the sum of certain correlation coefficients cannot exceed 2. But quantum mechanics predicts a maximum value of about 2.828. This difference is measurable. You can actually do the experiment and see which prediction nature follows. Let's think about this more concretely. Suppose particles have hidden properties that determine their behavior. When measured along angle A, a particle might be programmed to give result plus, along angle B, maybe minus, along angle C, maybe plus again. The particle carries these instructions with it, determining all future measurement outcomes. If both particles in an entangled pair carry such instructions, then the correlations between measurements depend on how often the instructions match. Bell proved that no matter what instructions the particles carry, and no matter how cleverly those instructions are chosen, the correlations must obey certain limits. These limits are what we call Bell inequalities. But quantum mechanics predicts correlations that exceed these limits. The quantum predictions involve the angle between measurement directions. The correlation depends on the cosine of twice the angle difference. This produces stronger correlations than any local hidden variable theory can achieve. The mathematical beauty of Bell's theorem lies in its generality. Bell didn't assume any specific hidden variable theory. His proof works for any theory that respects locality and realism. No matter how clever your hidden variable model, if it's local, it must obey the inequality, and quantum mechanics violates it. When Bell first derived his inequality, he was astonished. He had shown that the philosophical question raised by EPR could be answered experimentally. You could actually test whether Einstein or Bohr was right. This was unprecedented. Philosophical disputes don't usually have experimental resolutions. Bell's theorem was revolutionary because it transformed a philosophical question into an experimental one. You could actually test whether nature obeys Einstein's hidden variables or the strange predictions of quantum mechanics. The first experiments were performed in the early 1970s. Over the decades, the experiments became more and more sophisticated, closing various loopholes that skeptics pointed out. And the results were always the same. Quantum mechanics was right. Nature violates Bell's inequalities. One of the first major experiments was performed by John Clauser and Stuart Friedman at Berkeley in 1972. They used pairs of photons produced by excited calcium atoms. They measured the polarization of each photon along different angles and calculated the correlations. The results violated Bell's inequality, supporting quantum mechanics over local hidden variables. Clauser and Friedman's experiment was technically challenging. They had to produce many pairs of entangled photons and detect them efficiently. The detectors of that era were not very efficient, detecting only a small fraction of the photons produced. This opened a potential loophole. Maybe the photons that were detected were not representative of all the photons produced. But the early experiments had limitations. There were loopholes, possible ways that local hidden variables might still be able to explain the results. One loophole was that the detectors didn't always catch every photon. Maybe the photons that were detected weren't a fair sample. Another loophole was that the choice of which angle to measure could be predetermined, allowing the particles to coordinate their responses. Over the years, physicists designed better and better experiments to close these loopholes. In 1982, Alain Aspect performed a crucial experiment in Paris. He used fast-switching devices to change the measurement angles while the photons were in flight, making it impossible for them to coordinate in advance. The results still violated Bell's inequality. Aspect's experiment used acousto-optic switches that could redirect photons to different detectors in nanoseconds. The photons were separated by many meters, and the measurement choice was made while they were traveling. Even if information could travel at the speed of light, it couldn't reach from one photon to the other in time to coordinate their results. This closed the locality loophole. More experiments followed. In the 2000s, Anton Zeilinger's group in Vienna performed experiments with entangled photons over large distances. They sent photons through the air across the city, then later across the Danube River to different locations. No matter how far apart the measurements were, the correlations remained, and Bell's inequality was violated. Zeilinger's experiments pushed the boundaries of what was possible with entangled photons. They demonstrated quantum correlations over distances of hundreds of meters, then kilometers. These experiments showed that entanglement doesn't weaken with distance. Two particles can remain entangled no matter how far apart they are. as long as they don't interact with anything else. In 2015, 3 different teams performed what are called loophole-free Bell tests. These experiments closed all the major loopholes simultaneously. They used fast detectors, random measurement choices, and sufficient separation between the measurement sites. The results were conclusive. Nature really does violate Bell's inequalities. One experiment, performed at Delft University in the Netherlands, used electrons trapped in diamond crystals separated by more than a kilometre. The measurement choices were made by random number generators at each site. The detectors were fast and efficient enough to catch enough events to rule out the detection loophole. All conditions were satisfied, and Bell's inequality was violated by many standard deviations. This means that either hidden variables don't exist, or if they do, they must be non-local. The particles really do influence each other faster than light. Einstein's worst fear was confirmed. We are obliged to invoke something like actions going faster than light from one place to another. Bell's theorem is now considered one of the most profound discoveries in physics. It shows that the universe is far stranger than Einstein ever imagined. The discovery was about whether there was a problem, whether there was something to be concerned about, and the major concern that Einstein brought to the table from the beginning was about locality. What Bell showed was that all that stuff Einstein was concerned about, he was completely right to be worried about it. We have a problem. If these particles really are acting non-locally, shouldn't this cause paradoxes? Well, it does. But the paradox seems to be surprisingly tame. Imagine you and your friend are measuring a pair of entangled particles. Suppose an observer sees you measure yours first, and then your friend measures hers. That observer thinks that you collapsed the overall state of both particles, and your friend just found out the result when she measured. But another observer will see the situation in reverse. They see her measure first, and then you. To them, it was her measurement that caused the collapse, not yours. But who's right? Which measurement was the cause of the collapse, and which was the effect? It seems to depend on your frame of reference. This paradox is worrying, but it is not as bad as the usual faster-than-light paradoxes. In relativity, if you can communicate faster than light, then you can exploit how different observers disagree about timing. If your friend who's on a rocket sends you an instant message, and you send an instant message back, in some frames of reference, your message can arrive before she even sent the first one. If your message says, "Don't send your original message," and so she doesn't, then you have a paradox. What prompted you to send this message if she never sent you anything in the first place? These are called causal paradoxes, or grandfather paradoxes. If you could send information back in time, you could create logical contradictions. You could prevent the very event that caused you to send the message. The universe would become inconsistent. This is why faster-than-light communication is forbidden in relativity. It would allow time travel paradoxes. But quantum entanglement doesn't create these paradoxes. Why not? Because you can't use entanglement to send information. Quantum mechanics sidesteps these paradoxes through a fundamental constraint. The outcomes are random, so you cannot send messages faster than light. When you measure your particle, you get a plus or a minus, completely at random. Your friend measuring their particle also gets a random result. The results will be correlated, but they're still completely random, so there's no way to send any faster-than-light message this way. That's what prevents us from sending messages back in time using quantum mechanics. Think about it carefully. You measure your particle and get a random result. Your friend measures her particle and gets a random result. Later, when you compare notes, you discover that your results were correlated, but neither of you could predict what result you would get, and neither of you could use your measurement to send information to the other person. It's like having two magic coins that always land on opposite sides. Every time you flip yours and get heads, your friend's coin lands on tails. But you can't control which way your coin lands, so you can't use it to send a message. All your friend sees is a random sequence of heads and tails. Only when you compare sequences do you discover they were correlated. This no-signaling theorem is a deep result in quantum mechanics. The correlations between entangled particles are perfect, but they're also perfectly useless for communication. The randomness that troubled Einstein so much is exactly what prevents causal paradoxes. If quantum mechanics were deterministic, as Einstein wished, faster-than-light communication might be possible, leading to contradictions with relativity. So, quantum mechanics is non-local, but it does not lead to the sort of catastrophic paradoxes you might expect from relativity. It's an uneasy truce. Quantum mechanics may not break the letter of relativity's laws, but it certainly violates the spirit. And non-locality is not the only troubling thing about quantum mechanics. The Copenhagen interpretation still does not explain what an electron is really doing and why it acts so differently when measured. Despite this, many physicists took Bell's theorem to mean that the Copenhagen interpretation was right all along. Bell himself rejected this. He spent the rest of his life championing alternative interpretations of quantum mechanics, including a hidden variable interpretation called pilot wave theory, or Bohmian mechanics. Bell's theorem does not rule this interpretation out because pilot wave theory is non-local, just like the Copenhagen interpretation. Pilot wave theory was originally developed by Louis de Broglie in 1927, the same year as the Solvay conference. De Broglie proposed that particles are always particles, not waves, but they're guided by a real physical wave called a pilot wave. The particle follows the wave like a surfer riding an ocean wave. This wave is non-local, meaning it can instantly respond to distant changes. This allows pilot wave theory to reproduce all the predictions of quantum mechanics while maintaining that particles have definite positions at all times. The theory was largely forgotten for decades. Then in 1952, David Bohm rediscovered and refined it, giving it a more complete mathematical foundation. Bell was deeply interested in Bohmian mechanics because it showed that quantum mechanics didn't have to be interpreted in the Copenhagen way. There were alternatives that made sense, even if they required accepting non-locality. In pilot wave theory, the wave function is a real physical field that guides particle motion. The wave evolves according to Schrödinger's equation. Particles have definite positions and momenta at all times, unlike in Copenhagen. When you perform a measurement, you're simply learning what was already there. There's no mysterious collapse. The catch is that the pilot wave is non-local. It can instantly reconfigure itself across vast distances in response to changes anywhere. When you measure one particle in an entangled pair, the pilot wave throughout all of space instantly adjusts. This is how pilot wave theory explains the correlations that violate Bell's inequality. It was Bell's theorem and Bell's subsequent tireless work that made studying the meaning of quantum mechanics respectable again. He showed that mere armchair philosophy and thought experiments can have real consequences in physics. We need to be teaching quantum physics in a different way. We need to be teaching Bell's theorem in a different way. We do often teach Bell's theorem to physics students, and it's taught as something that rules out local hidden variables. That's just not true. Bell's theorem says that quantum physics is in very serious tension with relativity on the issue of locality. John Bell passed away suddenly at the age of 62. He did not know it, but he had been nominated for the Nobel Prize just a year earlier. Bell died of a cerebral hemorrhage in October 1990. His death was unexpected and shocked the physics community. Many felt that he deserved the Nobel Prize for his work on entanglement and quantum foundations. Some speculate that he would have shared the prize with Clauser, Aspect, and others who performed the experimental tests of Bell's theorem. In 2022, the Nobel Prize in Physics was indeed awarded to Clauser, Aspect, and Zeilinger for their experiments on quantum entanglement, though sadly, Bell was not alive to share in the recognition. The 2022 Nobel Prize citation recognized the experimenters for their experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. It was a vindication of Bell's vision. The work he considered most important, the work that many of his colleagues dismissed as philosophy, turned out to be foundational for an entire new field of physics. In a talk he gave in Geneva in January 1990, he said he thought we were stuck with non-locality. He did not know any conception of locality which works with quantum mechanics. That was 8 months before he died, so pretty much his last word on the subject. And so that's it. There really are faster-than-light influences in the universe. Bell's theorem proves it. But maybe there is a way out. There is another way to interpret quantum mechanics that's even more bizarre than the Copenhagen interpretation. Imagine the EPR thought experiment again. We can think of the entangled state as being in a superposition of the electron being up and the positron down, and the electron being down and the positron being up. In the Copenhagen interpretation, when you measure a particle and you get only one result, say plus, the other part of the superposition collapses. But in our examples, we've seen that measurement collapse seems to be the source of non-locality. So why don't we just get rid of collapse altogether? This is what the many worlds interpretation of quantum mechanics proposes. When you measure a particle, instead of you collapsing the particle to one outcome, both outcomes happen. And there are two parallel versions of you who see each outcome. You have become entangled with your particle because your state depends on what the particle is doing. The many worlds interpretation was proposed by Hugh Everett in 1957. He was a graduate student at Princeton at the time. His thesis advisor was John Wheeler, one of the giants of 20th century physics. Everett's idea was radical and controversial. Most physicists dismissed it as science fiction. How could there be multiple versions of you? How could you split into parallel worlds every time a quantum measurement occurred? But Everett's mathematics was sound. He showed that you didn't need to add wave function collapse to quantum mechanics. If you just followed the Schrödinger equation without interruption, branching naturally emerged. The universe continuously splits into parallel branches, one for each possible outcome of every quantum event. Everett called his interpretation the relative state formulation. The name many worlds came later, coined by physicist Bryce DeWitt, who championed the theory in the 1970s. DeWitt recognized the radical implications and wasn't afraid to state them clearly. Every quantum measurement splits the universe into multiple branches. All possible outcomes occur. We just experience one branch. It sounds strange, but there's one huge benefit of this interpretation. When your friend is about to measure her electron, your positron does not need to rush to tell the electron what the answer will be. There are already two versions of the electron, and they contain the right answer for each version of her. There was no need for faster-than-light communication to explain the EPR experiment. But how is that possible? Doesn't Bell's theorem prove that the two particles must communicate faster than light? Well, in Bell's proof, we assumed that all measurements have just one outcome. But that assumption just is not true in many worlds. This means that technically, that proof does not even apply in the many worlds case. This is a subtle but crucial point. Bell's theorem assumes that when you measure a particle, you get one definite result. The particle is either spin up or spin down, not both. This assumption is called the single outcome assumption. But in many worlds, both outcomes occur. There's a branch of the universe where the particle is spin up and another branch where it's spin down. You exist in both branches, though the two versions of you can't communicate with each other. Because both outcomes happen, there's no need for the distant particle to be instantly informed of the result. Both possible results exist in different branches, and they're already correlated correctly. The correlations don't require faster-than-light influences. They're built into the structure of the wave function from the beginning. So is many worlds local? In one sense, no, because just like in Copenhagen quantum mechanics, entangled pairs can be separated by a huge distance and still share their state. However, it is local, unlike Copenhagen, in the sense that these far-away entangled particles do not influence each other faster than light. Many worlds obeys Einstein's universal speed limit. But is it really worth accepting that there are many versions of you in parallel universes, just to recover locality? Well, locality is not the only reason many worlds has become more and more popular. Many physicists find the many worlds interpretation attractive because it takes quantum mechanics seriously at face value. There's no arbitrary division between the quantum world and the classical world. There's no mysterious collapse process. Everything follows the Schrödinger equation all the time. The universe is one giant quantum wave function evolving smoothly and deterministically. I also really like many worlds because Copenhagen never sits right. When you start telling the story of what happens at measurement, it's like, well, what is a measurement? When you have this quantum system and there's some other system which is much larger, it always feels a little bit arbitrary. Whereas this argument that every time two quantum particles are interacting, their wave functions are essentially combining and becoming entangled, that to me feels more consistent. Yes, but I think that's right. What do you think are the problems with many worlds? The biggest problem is that people struggle to deal with the infinity that it brings forth. But I don't know that that's necessarily an argument against it. Just because it's hard to imagine doesn't mean it's not what's happening. The many worlds interpretation does face conceptual challenges. One of the biggest is the question of probability. If all outcomes happen, why do some outcomes seem more probable than others? In standard quantum mechanics, the wave function amplitude gives you the probability of each outcome. But if all outcomes occur in different branches, what does probability even mean? This is called the probability problem in many worlds. Various solutions have been proposed. One approach uses decision theory. If you're making a bet on a quantum outcome, you should bet according to the quantum probabilities, even if all outcomes occur. Another approach uses the Born rule, which relates probabilities to the squared amplitude of the wave function. Deriving this from first principles in many worlds remains an active area of research. Another challenge is the sheer number of branches. Every quantum event causes the universe to split, and quantum events are happening everywhere, all the time. Atoms decaying, photons scattering, electrons changing states. Each one creates new branches. The number of branches grows exponentially, becoming unimaginably vast. Some find this ontological extravagance too much to accept. Yet supporters of many worlds argue that simplicity and elegance count for something in physics. Many worlds requires no extra postulates beyond the Schrödinger equation. You don't need to add collapse. You don't need to specify when or how measurements occur. The theory is simpler and more unified, even if its implications seem wild. If many worlds is right, everything changes. The conflict between quantum mechanics and relativity vanishes. Physicists have been struggling for decades to unite quantum mechanics with general relativity to build a theory of quantum gravity. And maybe we've been failing because we've been trying to marry relativity to a non-local theory. The quest for quantum gravity is one of the great unsolved problems in physics. General relativity describes gravity as the curvature of space-time. It works beautifully for large objects like planets and stars. Quantum mechanics describes the behavior of tiny particles. It works beautifully for atoms and electrons. But when you try to combine them, the mathematics breaks down. You get infinities and contradictions. One source of tension might be the non-locality of quantum mechanics. General relativity is fundamentally local. Effects propagate through space-time at the speed of light or slower. Nothing jumps from place to place instantaneously. But the Copenhagen interpretation of quantum mechanics requires non-local collapse. This clash between local space-time and non-local quantum mechanics might be preventing us from finding a unified theory. If quantum mechanics is actually local, as many worlds suggests, then this obstacle disappears. Space-time and quantum mechanics are both local. They both respect the speed of light limit. Maybe this is the key to unifying them. Several approaches to quantum gravity, including some versions of string theory and loop quantum gravity, work more naturally with a local interpretation of quantum mechanics. String theory attempts to unify all forces by proposing that fundamental particles are actually tiny vibrating strings. Different vibration modes correspond to different particles. In string theory, space-time itself emerges from the quantum behavior of these strings. Entanglement plays a crucial role in how space-time is woven together from stringy threads. Loop quantum gravity takes a different approach. It quantizes space-time directly, breaking it into discrete chunks at the Planck scale, about 10 to the negative 35 meters. Space-time becomes granular, made of tiny loops and networks. Quantum mechanics and gravity are unified because gravity is the quantum behavior of space-time itself. But if quantum mechanics ultimately turns out to be local, well then Einstein's dream of a local description of reality might not be dead after all. Einstein spent the last decades of his life searching for a unified field theory, a single framework that would explain all the forces of nature. He never succeeded, and many thought his quest was misguided. But perhaps he was right to insist on locality. Perhaps his intuition was guiding him toward a deeper truth. Today, quantum entanglement is not just a philosophical puzzle. It's become a practical resource. Scientists and engineers are building technologies based on entanglement that would have seemed like magic just a few decades ago. Quantum computing is perhaps the most famous application. Traditional computers store information in bits, which can be either 0 or 1. Quantum computers use quantum bits or qubits, which can be in a superposition of both 0 and 1 simultaneously. When you entangle multiple qubits together, they can perform certain calculations exponentially faster than classical computers. The power of quantum computing comes from quantum parallelism. A classical computer with 3 bits can represent 8 different numbers, but only one at a time. A quantum computer with 3 qubits can represent all 8 numbers simultaneously in superposition. As you add more qubits, the number of simultaneous states grows exponentially. 10 qubits can represent over 1,000 states at once. 20 qubits can represent over 1,000,000. 50 qubits can represent more states than there are atoms in Earth. This doesn't mean quantum computers are faster at everything. For many tasks, classical computers remain superior. But for certain specific problems, quantum computers have fundamental advantages. Searching large databases, factoring large numbers, simulating quantum systems. These tasks are exponentially hard for classical computers, but potentially tractable for quantum ones. Problems that would take a classical computer millions of years to solve might take a quantum computer just minutes. This has profound implications for fields like cryptography, drug discovery, and artificial intelligence. Companies like IBM, Google, and startups around the world are racing to build practical quantum computers. In 2019, Google announced they had achieved quantum supremacy. Their quantum computer performed a specific calculation that would be essentially impossible for any classical computer. The calculation itself wasn't particularly useful, but it demonstrated that quantum computers really can outperform classical ones. It was a milestone in the field. Google's Sycamore processor used 53 qubits to perform a calculation that would take the world's most powerful supercomputer approximately 10,000 years to complete. The quantum computer did it in 200 seconds. The calculation involved sampling the output of a random quantum circuit, essentially demonstrating that the quantum computer was working as expected and outperforming classical simulation. But quantum computing faces enormous challenges. Qubits are fragile. They lose their quantum properties through a process called decoherence. Any interaction with the environment, even stray photons or vibrations, can destroy the delicate quantum state. Building a large-scale, error-corrected quantum computer remains one of the great engineering challenges of our time. Current quantum computers are called noisy, intermediate-scale quantum devices. They have dozens to hundreds of qubits, but those qubits are noisy and error-prone. To build a truly powerful quantum computer capable of running useful algorithms, we need error correction. This requires many physical qubits to encode each logical qubit. Estimates suggest we might need thousands or millions of physical qubits to create a few hundred reliable logical qubits. Progress is steady. Companies are building larger quantum computers with better qubit quality. New error correction codes are being developed. The first demonstrations of quantum error correction in small systems have been achieved. But we're still years, perhaps decades, away from quantum computers that can solve real-world problems better than classical computers on a routine basis. Quantum communication is another application of entanglement. You can use entangled particles to create communication channels that are fundamentally secure. If anyone tries to eavesdrop on the communication, they inevitably disturb the quantum state, and you can detect their presence. This is called quantum key distribution. It's already being used in some secure communications. China has launched a quantum satellite called Misius that creates entangled photon pairs in space and sends them to ground stations thousands of kilometers apart. Banks and governments are exploring quantum communication to protect sensitive data. The security of quantum communication comes from the no-cloning theorem. You cannot make a perfect copy of an unknown quantum state. If an eavesdropper tries to intercept quantum information, they must measure it, which disturbs the state. The legitimate users can detect this disturbance and know their communication has been compromised. Several quantum communication networks are already operational. A network connects government and financial institutions in Beijing. Another connects major cities in Switzerland. These networks distribute encryption keys using quantum key distribution. The keys are provably secure, guaranteed by the laws of quantum mechanics rather than assumptions about computational difficulty. Quantum teleportation is another strange application. Despite the name, it doesn't involve moving matter from place to place. Instead, it transfers the quantum state of one particle to another distant particle using entanglement. The original particle's state is destroyed in the process, but the distant particle becomes an exact copy. This might sound like science fiction, but it's been demonstrated many times in laboratories. In 2017, Chinese scientists used their Messias satellite to teleport a quantum state from Tibet to a satellite orbiting overhead, a distance of about 1,400 kilometers. It's the longest distance quantum teleportation ever achieved. Quantum teleportation works by combining entanglement with classical communication. You start with an entangled pair of particles, one with the sender and one with the receiver. The sender performs a special measurement that entangles the particle they want to teleport with their half of the entangled pair. This measurement produces some classical information which is sent to the receiver. The receiver uses this information to perform an operation on their particle, transforming it into a copy of the original state. The no signaling theorem still applies. Information doesn't travel faster than light. The classical message must be sent through normal channels. But the quantum state is transferred in a way that would be impossible classically. This technique is essential for building quantum networks and distributed quantum computers. Beyond communication and computing, quantum entanglement enables incredibly sensitive sensors. Quantum sensors can detect magnetic fields, gravitational fields, time, and other quantities with precision far exceeding classical sensors. These devices exploit quantum superposition and entanglement to achieve sensitivity at the fundamental quantum limit. Atomic clocks, already the most precise timekeeping devices, are being improved with quantum entanglement. Traditional atomic clocks measure the frequency of light absorbed by atoms. Quantum limits impose fundamental precision boundaries. But by entangling multiple atoms, physicists can beat these limits. Entangled atomic clocks could be 10 times more precise than current standards. Such precision has practical applications. GPS relies on atomic clocks. Better clocks mean better navigation. Precise timekeeping is also essential for synchronizing telecommunications networks and power grids. Scientific research benefits too. Detecting gravitational waves requires exquisite timing. Searching for dark matter and testing fundamental physics need the best possible clocks. Quantum magnetometers can detect incredibly weak magnetic fields. Medical applications include better brain imaging. Geological applications include mineral exploration. Military applications include submarine detection. These sensors exploit the quantum properties of atoms or diamond defects to measure fields millions of times weaker than Earth's magnetic field. Quantum gravity sensors could revolutionize geology and civil engineering. By precisely measuring local gravity, these sensors can map underground structures. They can detect hidden tunnels, mineral deposits, groundwater, and even archaeological sites. Traditional gravity surveys require expensive equipment and long measurement times. Quantum sensors promise to be faster, more portable, and more sensitive. All these applications rely on the strange non-local correlations that Einstein found so troubling. The very feature of quantum mechanics that seemed like a bug has turned out to be a feature we can exploit. What Einstein saw as a flaw is now seen as a resource. Yet the fundamental questions remain. What is really happening when particles become entangled? Are they connected by something physical? Or is entanglement telling us that our concepts of space and separateness are somehow incomplete? Some physicists believe that entanglement is more fundamental than space itself. They suggest that space-time might emerge from quantum entanglement. In this view, the fabric of space is woven from countless entangled quantum threads. Distance and separation are illusions that emerge at large scales. This idea is actively being explored in approaches to quantum gravity. The AD-SCFT correspondence, a conjecture from string theory, suggests a deep connection between quantum entanglement and the geometry of space-time. When particles become more entangled, the space-time connecting them becomes more connected. When entanglement decreases, space pulls apart. In ad SCFT, space-time in a higher dimensional universe is mathematically equivalent to quantum field theory in a lower dimensional boundary. This correspondence has been incredibly fruitful for theoretical physics. It allows calculations in one framework to be translated to the other. And crucially, it shows that entanglement in the quantum theory corresponds to connectivity in the space-time geometry. Physicist Mark van Ramsdonk proposed that space-time is held together by quantum entanglement. Without entanglement, space-time would fragment into disconnected pieces. The amount of entanglement determines how strongly different regions of space are connected. This suggests a radical idea. Space itself is made of entanglement. These are speculative ideas, but they point to a radical possibility. Perhaps space and time are not fundamental aspects of reality. Perhaps they're emergent properties that arise from something deeper. And that something might involve quantum entanglement. Einstein's discomfort with entanglement led him to search for a deeper theory. He believed quantum mechanics was incomplete. Perhaps he was right, though not in the way he expected. The deeper theory might not eliminate entanglement. Instead, it might explain space itself in terms of entanglement. The philosophical implications of quantum mechanics extend beyond physics. They touch on questions about the nature of reality, observation, and consciousness. Some interpretations of quantum mechanics suggest that observation plays a fundamental role in creating reality. In the Copenhagen interpretation, the wave function collapses when a measurement is made. But what counts as a measurement? Does it require a conscious observer? Or is any interaction with the environment sufficient? These questions led some physicists to speculate about connections between quantum mechanics and consciousness. The most famous exploration of this is Schrödinger's cat thought experiment. Imagine a cat in a sealed box with a vial of poison connected to a quantum device. The device has a 50% chance of breaking the vial within an hour. According to quantum mechanics, after an hour, the cat is in a superposition of alive and dead states. Only when you open the box and observe does the wave function collapse to one outcome or the other. Schrödinger proposed this to highlight the absurdity, as he saw it, of applying quantum mechanics to macroscopic objects. Surely the cat is either alive or dead, not both. But when exactly does the superposition collapse? When you open the box? When light from the cat enters your eye? When the signal reaches your brain? When you become conscious of seeing the cat? Schrödinger himself became deeply troubled by quantum mechanics in his later years. He had developed the wave equation that bears his name, one of the foundational equations of quantum mechanics. Yet he grew to dislike the probabilistic interpretation of his equation. He preferred to think of the wave function as representing a real physical wave, not just probabilities. In 1935, the same year as Einstein's EPR paper, Schrödinger published several papers exploring the implications of quantum entanglement. He coined the term entanglement and recognized it as the defining feature of quantum mechanics. But rather than embracing this strangeness, Schrödinger found it deeply unsettling. He believed it revealed a fundamental problem with the theory. Schrödinger corresponded extensively with Einstein during this period. They shared similar concerns about quantum mechanics and encouraged each other's skepticism. In letters, Schrödinger expressed his discomfort with the Copenhagen interpretation and his hope that a better understanding would emerge. Like Einstein, he believed quantum mechanics must be incomplete. Yet Schrödinger's equation remains central to quantum mechanics. Every quantum system evolves according to his equation. It describes atoms, molecules, solids, quantum computers, everything. The equation works perfectly. It's the interpretation that troubled Schrödinger, not the mathematics. His creation succeeded beyond his imagining, even if he questioned what it meant. Most physicists today believe that consciousness is not special in quantum mechanics. Decoherence, the process by which quantum systems become entangled with their environment, explains why we don't see quantum effects in everyday life. A measurement is just a special case of decoherence. No consciousness required. The cat is constantly interacting with air molecules, photons, and other environmental particles. These interactions entangle the cat with its environment, effectively measuring it continuously. Decoherence happens almost instantly for objects as large as cats. The superposition is destroyed long before any conscious observer looks. The cat is either alive or dead, determined by when the quantum device triggered, not by when someone observes. Decoherence theory, developed in the 1970s and 80s, provides a detailed mathematical description of how quantum systems lose their quantum properties through environmental interaction. It explains the emergence of classical behavior from quantum mechanics without invoking collapse or consciousness. The quantum world doesn't disappear. It just becomes incredibly difficult to observe quantum effects in large systems. But the questions persist. The measurement problem, as it's called, remains controversial. At what point does a superposition become a definite outcome? Is there a precise boundary between the quantum and classical worlds? Or is it all quantum, as many worlds suggests? Different interpretations give different answers. In Copenhagen, measurement is fundamental but mysterious. In many worlds, there is no measurement, only branching. In pilot wave theory, particles always have definite positions, and measurement just reveals what was already there. There are other interpretations too. Objective collapse theories propose that the wave function spontaneously collapses at random, with the rate depending on the size or energy of the system. Small particles rarely collapse. Large objects collapse almost instantly. This would explain why we don't see cats in superposition while preserving quantum behavior for small particles. The debate over interpretation is not just philosophical navel-gazing. It shapes how physicists think about new theories and experiments. It influences which questions seem worth pursuing and which seem meaningless. The interpretation you favor can affect your scientific intuition. For decades, talking about interpretations was considered unscientific. The attitude was, shut up and calculate. Don't worry about what quantum mechanics means, just use it to make predictions. This pragmatic approach worked well for developing technology and solving practical problems, but it left fundamental questions unanswered. Bell's work changed this. He showed that interpretational questions could have experimental consequences. He made it respectable to think deeply about what quantum mechanics is telling us about reality. Today, quantum foundations is a thriving field of research. Physicists are developing new experiments and new theories to probe the nature of quantum reality. One active area of research involves testing quantum mechanics in increasingly extreme conditions. Most tests of quantum mechanics involve small particles, like photons or electrons. But does quantum mechanics apply to larger objects? Where is the boundary, if there is one, between quantum and classical? Physicists are creating quantum superpositions of larger and larger objects. Molecules with hundreds of atoms have been put into superposition. Researchers are working toward putting viruses and even tiny mirrors into quantum states. These experiments test whether quantum mechanics really applies to everything, or if there's some modification at larger scales. One approach uses matter wave interferometry. Molecules are sent through a double-slit type setup, creating interference patterns that demonstrates superposition. The current record involves molecules with over 2,000 atoms showing quantum interference. Researchers are pushing toward even larger molecules, testing the limits of quantum mechanics. Another area explores the connection between quantum mechanics and gravity. General relativity and quantum mechanics are both incredibly successful theories, but they seem fundamentally incompatible. Combining them is one of the great challenges in physics. Some approaches, like string theory and loop quantum gravity, try to quantize gravity. They treat space-time itself as quantum mechanical. Other approaches suggest that quantum mechanics might need to be modified when gravity becomes important. Testing these ideas requires experiments at the intersection of quantum mechanics and gravity. One proposal involves putting small masses into quantum superposition and looking for gravitational effects. If a particle is in two places at once, does its gravitational field split too? Or does gravity somehow force the particle to be in one place? These are questions we don't yet know how to answer. Experiments are being developed to put tiny mirrors or masses into quantum superposition and look for gravitational signatures. The challenge is that gravity is incredibly weak for small masses. The gravitational self-interaction of even a large molecule is tiny compared to other forces. But with sufficiently sensitive experiments, we might be able to probe the quantum nature of gravity. The search for a theory of quantum gravity is also connected to some of the deepest mysteries in cosmology. What happened at the Big Bang? What is inside a black hole? What is dark matter and dark energy? All these questions involve physics at scales where both quantum mechanics and gravity are important. The black hole information paradox is a famous puzzle at the intersection of quantum mechanics and gravity. When matter falls into a black hole, what happens to the quantum information it carries? Hawking showed that black holes radiate and eventually evaporate, but the radiation appears to be thermal, carrying no information about what fell in. This would violate quantum mechanics, which says information cannot be destroyed. Recent work suggests the information is not lost, but encoded in subtle correlations in the Hawking radiation. Understanding this requires combining quantum mechanics and gravity in new ways. It may require thinking about space-time differently, perhaps as emergent from entanglement. If we can reconcile quantum mechanics with general relativity, we might unlock the answers to these cosmic mysteries. And locality plays a crucial role in this quest. If quantum mechanics is fundamentally non-local, that might conflict with the local structure of space-time in relativity. But if many worlds is correct, and quantum mechanics is actually local, then the path forward might be clearer. Looking back at the century-long journey from Einstein's discomfort to modern quantum technologies, we see how science progresses. Einstein identified a genuine puzzle about the nature of quantum mechanics. Bohr responded with a philosophical framework that worked for practical purposes, but the puzzle didn't go away. Bell transformed it into a testable question. Experiments confirmed the strange predictions. And now we're learning to harness these strange effects for technology. The story is not finished. We still don't fully understand what quantum mechanics is telling us about reality. The measurement problem remains. The interpretation debate continues. New experiments may reveal surprises. And the quest for quantum gravity may force us to revise our understanding once again. But we've come a long way from the 1927 Solvay conference. We've moved from philosophical debates to experimental tests to practical applications. We've learned that the universe is stranger and more wonderful than anyone imagined. And we're beginning to glimpse the outlines of an even deeper understanding waiting to be discovered. The next decades promise exciting developments. Larger quantum computers will tackle problems beyond classical reach. Quantum communication networks will span continents. Tests of quantum mechanics at larger scales and stronger gravitational fields will probe the boundaries of the theory. New experiments testing different interpretations may finally resolve century-old debates. Climate modeling requires simulating incredibly complex systems. The atmosphere, oceans, ice sheets, vegetation, all interact through countless feedback loops. Current models run on supercomputers and still can't capture all the details. Quantum computers might simulate climate systems more accurately, improving our ability to predict and respond to climate change. And somewhere in all this progress, we may find the key to quantum gravity. We may understand how space-time emerges from quantum entanglement. We may discover whether many worlds is correct, whether we really do split into parallel branches with every quantum event. We may finally understand what the wave function represents and why measurements seem so special. Progress in quantum gravity is accelerating. String theory has made connections between gravity and quantum field theory through dualities. Loop quantum gravity has developed a detailed picture of quantum spacetime. Other approaches, like causal set theory and asymptotic safety, offer alternative paths. The problem is fiendishly difficult, but physicists are making steady progress. One exciting development is the holographic principle. This proposes that all the information in a volume of space can be encoded on its boundary. It sounds like science fiction, but emerges naturally from black hole thermodynamics and string theory. If true, it suggests that three-dimensional space is somehow a projection of information stored on a two-dimensional surface. This could fundamentally change how we think about space-time. The black hole information paradox drove much of this progress. When Stephen Hawking showed that black holes evaporate, releasing thermal radiation that carries no information, it created a crisis. Quantum mechanics says information cannot be destroyed. Something had to give. Recent work suggests the information is preserved in subtle quantum correlations in the Hawking radiation. Understanding this required new insights about quantum entanglement and space-time structure. Experiments testing quantum mechanics at the largest scales involve cosmology. The cosmic microwave background, the afterglow of the Big Bang, may carry signatures of quantum fluctuations in the early universe. These primordial quantum fluctuations, stretched to cosmic scales by inflation, seeded the formation of galaxies. By studying the patterns in the cosmic microwave background, we're effectively observing quantum mechanics at work in the first moments of the universe. The story of quantum mechanics and locality is still unfolding. We've learned that nature is stranger than Einstein imagined, yet perhaps not quite as strange as the Copenhagen interpretation suggests. The universe may contain hidden depths we're only beginning to understand. And in those depths, Einstein's dream of a local, comprehensible reality might still be waiting to be discovered. Perhaps the ultimate theory will vindicate aspects of both Einstein's and Bohr's views. Perhaps reality is both local and complete, as Einstein hoped, but in a way that requires many worlds branching. Perhaps space and time are illusions emerging from deeper quantum reality. Perhaps consciousness plays no special role, yet the universe splits with every measurement, creating countless parallel experiences. What would a final theory look like? Nobody knows. But it would need to explain why quantum mechanics work so well, why general relativity works so well, and how to reconcile them. It would need to explain the origin of space-time, the nature of time, the arrow of time that distinguishes past from future. It would need to explain why the universe has the laws it does, why certain particles exist with their specific properties. Some physicists believe the final theory will be staggeringly simple, perhaps a single equation that fits on a t-shirt. Others think it will be irreducibly complex, involving structures beyond our current mathematical frameworks. Still others question whether a single final theory even exists. Maybe reality has layers upon layers, each requiring its own description. We cannot yet say what the final answer will be, but we know the question is real. Bell proved it, experiments confirmed it, and the quest continues. In laboratories around the world, physicists are probing the quantum nature of reality with ever greater precision. In offices and on blackboards, theorists are developing new frameworks to understand what it all means. Young physicists entering the field today have opportunities their predecessors could only dream of. Quantum computers exist, if only in primitive form. Quantum communication networks operate commercially. Experiments routinely create and manipulate entangled states. Tests of quantum mechanics probe ever more exotic regimes. The tools available for studying quantum foundations have advanced tremendously. Educational approaches are changing too. Students now learn quantum mechanics alongside its interpretations. The shut up and calculate mentality is fading. Questions about meaning and interpretation are taken seriously. Bell's theorem is taught early, recognized as central to understanding quantum mechanics. The next generation of physicists will approach these questions with fresh perspectives and better tools. International collaboration drives progress. Physicists from every continent contribute to advancing quantum science. The largest experiments require teams spanning multiple countries. Theoretical breakthroughs often come from unexpected collaborations between different research traditions. The quantum revolution is truly global. The journey from Einstein's thought experiments to modern quantum technology has been long and surprising. It has transformed our understanding of nature and enabled revolutionary new capabilities. But in the deepest sense, the journey is just beginning. The quantum mystery, the puzzle of how the universe truly works at its most fundamental level, remains unsolved. And that mystery might be the most profound and beautiful thing of all. Einstein's quest for a comprehensible, local, deterministic reality drove much of 20th century physics. His objections to quantum mechanics, once dismissed, turned out to raise genuine issues. Bell showed that locality and quantum mechanics are in deep tension. Experiments proved Einstein's concerns were justified. Yet quantum mechanics survived and thrived. Perhaps Einstein would have been satisfied with many worlds. It's local, deterministic, and requires no mysterious collapse. The price is accepting parallel universes, but Einstein was no stranger to radical ideas. He revolutionized our understanding of space, time, and gravity. He might have embraced the many worlds interpretation if he'd lived to see Bell's theorem and its experimental confirmation. Or perhaps not. Einstein's philosophical commitment to a single, definite reality was deep. The idea that every quantum measurement splits reality into branches might have troubled him as much as instantaneous collapse did. We can only speculate about what he would have thought. What we can say is that Einstein's legacy endures. His demand for conceptual clarity, his insistence on understanding, not just calculating, his faith that nature makes sense at the deepest level. These attitudes continue to inspire physicists today. The debate he started with Bohr continues, more sophisticated and informed by experiments, but fundamentally about the same questions. What is real? What can we know? How does nature truly work? Quantum mechanics teaches us that nature is far stranger than common sense suggests. Particles can be in two places at once. Measurements affect distant objects instantly. The act of observation changes what we observe. Reality at the quantum level defies our everyday intuitions. Yet quantum mechanics is also the most successful scientific theory ever created. Its predictions have been verified to extraordinary precision in countless experiments. This combination of strangeness and success is what makes quantum mechanics so fascinating and so frustrating. It works brilliantly, but we don't fully understand why. It makes predictions we can test, but those predictions seem to violate our deepest assumptions about how reality should work. A century after its development, quantum mechanics remains mysterious at its core. The quest to understand quantum mechanics is ultimately a quest to understand reality itself. What exists? How do things interact? What is the relationship between observer and observed? These are not just technical questions for specialists. They touch on fundamental aspects of existence that have puzzled philosophers for millennia. Physics has always been about understanding the fundamental nature of reality. From ancient Greek atomists to medieval scholars to modern scientists, humans have sought to comprehend the world around us. Quantum mechanics represents our deepest understanding yet, but it also reveals how much we still don't know. The universe is far more mysterious than we once imagined. As we look to the future, we can be certain of only one thing: the journey of discovery will continue. New experiments will probe quantum mechanics in new ways. New theories will offer new perspectives. New technologies will emerge from quantum foundations. And perhaps, someday, we will truly understand what quantum mechanics is telling us about the nature of reality. Until then, we continue to explore, to question, and to wonder at the magnificent strangeness of the quantum world.